Progressive JPEG continue. Hybrid progressive algorithm combines spectral selection and successive approximation. Here, scan 1, scan 2, scan 3, scan 4. Correspondingly, scan 1 DC band 1, scan 2 AC band 1, scan 3 AC band 2, scan 4 AC band 3, scan 5 AC band 4, scan 6 AC band 5, scan 7 DC band 2, scan 8 AC band 6. Here in yeah, in x direction dct coefficients 0, 1, 2. In y direction 0, 1, 2 bits. Here DC band 1, DC band 2, AC band 1. This is AC band 6. This is DC band 2, DC band 1, DC band 2, AC band 1, AC band 2, AC band 3. This area AC band 4, this area AC band 5, this area AC band 6. Here 0, 1, 2. Hierarchical JPEG. Hierarchical mode encodes the image at a different resolutions. Image is transmitted in multiple passes with increased resolution at each pass. Hierarchical JPEG block diagram for hierarchical JPEG n by 4 x cross n by 4 here n by 2 cross n by 2 here n cross n. In hierarchical JPEG block diagram hierarchical JPEG 4 2 encode decode f4 f4 given to encode output f4 given to decode, then f cap f, sorry, f cap 4 in from this encode decode given to 2, the symbol for encode, the symbol for decode. So decode f cap 4 here. This is so this is summation. Here 2 cap, sorry, 2 encode f2 given to the summation after this encode here given to t code d cap c is a d approximation. Here this d2 equal to f2 minus e of f approximation f4 approximation. Here d2 given to d code given to summation d2 approximation f2 approximation equal to e f f4 approximation plus d2 approximation. Here encode decode after summation f2 approximation, then this is 2 up, here do down 4 down. So decode up 2 up only given. So here f coming to summation. Then it is given to encode here D1. So this area full here decode. This area full encode we can say. So in between 4 n by 4 cross n by 4 n by 2 cross n by 2 is f f4 approximation, f2 approximation, e e of f4 approximation plus d2 approximation. Here decode d1 approximation summation in between n cross n by 2 cross n by 2 2 for up. So here f approximation equal to e of f2 approximation plus d1 approximation. Relative data redundancy. Let B and B dash denote the number of bits in two representation of the same information. The relevant data redundancy R equal to 1 minus 1 by C. C is called the compression ratio defined as C equal to B by B dash. Example C equal to 10. The corresponding relative data redundancy of the larger representation is 0.9, indicating that 90% of its data is redundant. Why do we need compression? Data storage, data transmission. How can we implement compression? Coding redundancy. Most 2D, that is two-dimensional intensity arrays contain more bits than are needed to represent the intensities. The spatial and temporal redundancy. Pixel of most 2D two-dimensional intensity arrays are correlated spatially and the video sequences are temporally correlated. Irrelevant information. Most two-dimensional intensities arrays contain information that is ignored by the human visual system. Examples of redundancy: computer generated 256 cross 256 cross 8 bit images with a coding redundancy, B spatial redundancy, C irrelevant information. Each was designed to demonstrate one principal redundancy but may exhibit others as well. Coding redundancy. Example of variable length coding: RK, PR RK, code 1, I1 of RK, code 2, I2 of RK. Here R87 equal to 87, PR of RK 0.25, code is 01010111, and then L1 of RK 8, code to 01, L2 of RK 2. The average number of bits required to represent each pixel is L average equal to summation of k equal to 0 to L minus 1, L of RK, PR of RK equal to 0.25 of 2 plus 0.47 of 1 plus 0.24 of 3, 0.03 of 3 equal to 1.81 bits. C equal to 8 by 1.87, approximately 4.42. R equal to 1 minus 1 by 4, 0.42 equal to 0.774. Spatial and temporal redundancy. All 256 intensities are equally probable. The pixels along each line are identical. The intensity of each line was selected randomly. This full area PR of RK here 1 by 256. In this K area 0, 50, 100, 150, 200, 250, 0, 250, 256, NK. The intensity histogram of the image in figure B. spatial and temporal intensity, all 256 intensities are equal probable. The pixels along each line are identical. The intensity of each line was selected randomly. Run length pair specifies the start of a uh, new intensity and the number of consecutive pixels that have that intensity. Each 256 pixel line of the original representation is replaced by a single 8-bit intensity value and length 256 in run length representation. The compression ratio is 256 2 into 256 into 8 divided by 256 plus 256 into 8 equal to 182 colon 1. Irrelevant information, number of pixels here, number of pixels here, 0, 50, 100, 150, 200, 256. Histogram of image, histogram of image A, and then histogram of a histogram equalized version of the image. 256 cross 256 cross 8 divided by 8 equal to 65536 65,000 65,536 ratio 1. Measuring image information. A random event E with the probability P of E is said to contain I of E equal to log 1 by P of E equal to minus log P of E units of information. Measuring image information given a source of statistically independent random events from a discrete set of possible events A1, A2 up to AJ with the associated probabilities P of A1, P of A2 up to P of AJ. The average information per source output called the entropy of the source H equal to minus summation over J equal to 1 to J P of AJ log P of AJ. AJ is called a source symbols. AJ is called the source symbols because they are statistically independent. The source called a memory zero memory source. Measuring image information, uh, if an image is considered to be the output of uh, imaginary zero memory intensity source, we can use the histogram of the observed image to estimate the simple probabilities of the source. The intensity sources entropy becomes H equal to minus summation over k equal to 0 to L minus 1 PR into RK log PR RK. PR of RK is the normalized histogram. Measuring image information for the figure 8.1a H equal to minus of 0.025 log 2 base to 0.25 plus 0.47 log 2 base to 0.47 plus 0.25 log base to 0.25 plus 0.03 log to 0.03 approximately equal to 1.6614 bits per pixel. Fidelity criteria, let f of xy be an input image and f cap of xy be an approximation of f of xy. The images are of size m cross n. The root mean square array is ERMS equal to 1 by mn summation of x equal to 0 to m minus 1 summation or y equal to 0 to n minus 1 f cap of x minus y minus f of xy whole square total whole square equal to 1 by 2. The mean square fidelity criteria, the mean square signal to noise ratio of the output image denoted SNR ms equal to yeah, summation over x equal to 0 to m minus 1 summation over y equal to 0 to n minus 1 of f capture of xy whole square divided by summation over x equal to 0 to m minus 1 summation over y equal to 0 to n minus 1 f cap into f cap of xy minus f